We are moving on to non-gradient based optimization this week. Today is April 21st. Okay, so we are moving on to evolutionary optimization. Okay. And the most well-known method in evolutionary optimization is genetic algorithm. It's so popular in many of your projects. You have GA, right? It's very simple, easy to use. When do we use GA? So usually when you have a problem that is, for example, a non-convex problem, basically concave. So if you have a function like this, okay, it's just an illustration based on a 1D problem. So over here, you have a global minimum, and you have a lot of local minimum. If you use gradient-based approach, you may get trapped into a local minimum. The gradient-based method doesn't know what's going on somewhere else. So if you are not lucky enough, you may get trapped at the local. So GA is not afraid of concave problem like this, because all kinds of evolutionary optimization relies on some kind of random process. And those random processes usually will spread out in the design space randomly, and usually this kind of process includes multiple, you can say, searching agent. They search around, okay? So when you have multiple searching points, you may be lucky enough, and some of the searching points can fall into a region that is closer to the global minimum. So if you have problems that is concave, GA may be one solution. Another kind of problem is discrete. For example, X must be integer. If X must be integer, 1.5 is not allowed, right? And if you want to do gradient at certain point, let's say at x equals to 2, and you try to use finite difference, delta you use 0.1, and you have f of 2.1 minus f of 2. And this one is violating what you are looking for, because you said x can only be integer. So it's possible that f of 2.1 doesn't exist in your problem. You cannot have 2.1 people, right? When you are counting something, usually it's an integer. So for discrete problems, You cannot take a gradient. Then how can you solve by gradient-based approach? Okay? Sometimes what people do is they will smoothen the function. Okay? They will smoothen the discrete method, make the discrete function continuous. So in their math problem, they allow 2.1 people. They just solve it. And at the end, maybe the optimal is 3.4 people. Then they will round the number at the final step. That is one way. You make your problem continuous artificially, and then discretize it at the end. But if you do that, you cannot guarantee the continuous process is gonna affect the result. You are not sure. Okay? Earlier we mentioned KKT conditions. You may think, okay, I can use KKT conditions to check whether my new solution is optimal. You cannot, because KKT condition is only good for continuous problems. Inside KKT conditions, there's gradient. Okay, so discrete problems is an issue, but GA doesn't care, is not worried about discrete problems. Okay, let me see what else. Okay, so sometimes there are decisions that cannot be quantified easily. So let's say you are trying to make a decision whether you are going to buy something, like choices. You have 3 different things to buy. And are you going to use a car to drive, or are you going to take the train, or are you going to walk? Those are decisions. And in reality, you don't quantify them, right? They are just choices. Of course, you can number them. Okay, number 1 choice, number 2 choice, number 3 choice, but those numbers doesn't mean anything. They are just they're just numbers you manually assign. And the magnitude of the numbers you put into those decisions sometimes doesn't even mean anything. But when you convert those choices into numbers, it may do something to your math process. So in GA, sometimes we also handle choices. So what does GA do? Actually, in fact, GA asks you to number them. So assign numbers to choices. Okay? But is it going to, let's say, choice number 1, choice number 2, or 3, is the magnitude going to affect the chances of those choices to be chosen? Not so much. So I think it is okay for GA to give numbers to choices. You don't even need to sort them in a certain way, because they have, I think, a similar probability of being chosen. Okay. Okay. So I think these are the 3 kinds of issues that gradient-based approach cannot handle, but GA can handle it. So let's talk about GA. What do we do? So usually, what the GA has so many versions. Okay, I'm just going to tell you the common and usual way, and there are so many small steps you can actually modify by yourself. Even when different papers or authors or programmers try to prepare their own GA, maybe inside their codes they have slight difference, but when they report them, they don't talk about such a small detail. So on paper, on written descriptions, they look the same. But in the program itself, there are usually so many small details it won't be reported. Okay, so when you read a paper about GA, sometimes the information is not fully provided. Okay. So anyway, I will try my best to show you the most common way, and later on when you do projects, if you really want to use GA, you need to define your own way to do your programming. So usually, the first step is to binarization of everything. So let's say we are solving a problem. If we are minimizing some f of x and we have certain constraints, and there are some rules about the variables. All the x, they are integer. So for this particular problem, it's difficult to solve by gradient-based approach. Okay. And sometimes you may have variable bounds, like lower bounds and upper bounds, something like that. So how do you binarize everything? The way you design the problem matters a lot. Even the same problem, different programmer, different designer can be defining the GA format differently. Okay. So for me, let's say I would like to use 8 digits to define, or 10 digits to define xi. So for every xi, I would like to use, let's say how many? 8 digits. 8 bits. Okay, so they could be 8 zeros and binary. So you add 1, then you end up with 7 zeros and 1. You add 1 again, it becomes 1 0, right? So it's a binary code. The last one would be 8 different ones. So in total, how many combination? There is a 2 to the 8th combination. So if you binarize xi in a certain way, that means one of it is your optimal. And if you binarize this xi in this way, this is the accurate. The accuracy is defined by how many digits you choose. You are the random process is going to choose one combination out of the 2 to the power of 8. Okay? If you want greater accuracy, you need more digits. So if you convert this to decimal, this is 0, this is 1, this is 2, and this is how many? 2 to the 9th is 512. So this should be 511. Is it? 512 minus 1, right? Yeah. So totally there are. No, I'm wrong. 255. Yes, 255. Yes. So there's totally 256 of them. So, but what does it represent? You can claim, okay, this is your lower bar, and this is your upper bound, lower bound and upper bound. So you are going to linearly transform those decimal numbers to your original bounds. Okay, so let's say, in fact, xi ranges from 2 to, let's say, 10. So you are going to do some conversion. Whenever you have 8 zeros, you are going to linearly map it to a real number 2. And then when it's 255, you are going to linearly map it to 10. So basically, you divide the interval from 2 to 10 into 256 different numbers. And your accuracy would be the 1 out of 256 within this interval. That's your accuracy. Okay? So that's the idea. This is one thing you can binarize. If you have decisions, let's say there are choices, and if you have choices of first kind, second kind, let's say 4 different kinds, then you can use 2 digits to define the choices, and you are going to occupy 2 digits for the choices of A to D. So you could be using 2 digits for this choice. Okay? So in this problem, there's going to be many of those binarized digits that you are going to use, and there are many of them. So now you are going to put them together into a very long string of zeros and ones. Are the orders matter? Does the order matter? Actually, not so much. But if you decide to pick up certain order, that's the order you choose for your coding. Okay, and usually in your research paper, if you want to report the results, you need to tell them how does the binarized digits are being defined, what's the order of them. So at the end of the result, sometimes you show a string of 0 and 1s, so people can go back and see the original definition. So when you combine all these together, now we are going to put in the genetic story into the optimization process. So there are going to be names that is from the genetic logic. So when you put all of these together, So there could be n's of digits. Okay? And they're all 0 or 1s. Okay? We call one string of this as a chromosome. So what in Chinese, what does chromosome mean? It means 染色体. Okay, for Taiwanese. But for the foreigners, I don't know how to explain. If you have no idea, if you fail biology, then I have no idea how to explain. So it's called the chromosome. Basically, the long string of biological codes in your DNA chromosome. Okay, so once you define your problem, everything that you want the computer to find, you binarize them and put them together in a certain order. You fix the format, but the 0 and 1s are to be chosen by computer. So how many choices are there in your entire solution set? 2 to the power of n combinations. This is basically your entire solution set. Okay? You won't be finding solutions out of this solution set. If you need more, then you need to redefine your entire chromosome and then prepare more digits. Okay? Otherwise, at the beginning, you have to define it. Now, where does the random process come from? At the initial stage, you will be asking the computer to randomly generate certain amount of chromosomes. So for every batch of these random chromosomes, let's say 10 of them or 100 of them, we call these as your like a generation. Okay. So here's a terminology inside GA, right? Chromosome, GA, and now we have a terminology called generation and population. Okay, so generation is just like an iteration. So when we say in the first generation, it's like a first iteration. So what's the population? Population usually is a number, and it's like how many random chromosomes you generate in each generation. So this is like a number of random chromosomes in each generation. Okay? We call population. And usually it's a fixed number. So let's say it's a number of capital M. Okay? So since you have n different digits, you are going to randomly generate m populations. So you are going to generate m times n random 0 and 1s at the first generation. Okay? And usually what you are going to do next is to check feasibility. Because if you randomly generate something that is not feasible, then this particular chromosome is having bad genes. It's like those chromosomes are DNA for different kinds of animals. And if you randomly generate some kind of bad DNA, this kind of animal doesn't survive the world. like a mutant which will die in 2 days, something like that. It cannot survive the world. So for that kind of infeasible design, you can delete those infeasible chromosomes at the beginning. Okay, so this is where your programming could be different from others. Some people like to keep the infeasible ones. Some people would like to kill the infeasible ones. It really depends. Because maybe the design is infeasible now, but maybe some numbers inside is good for future process. So it really depends on how you treat those infeasible designs. But in my experience, usually at this stage, if it's an infeasible design, you just get rid of it. So you have M random designs. Right here, after checking feasibility, you may be eliminating some of the random design out of the M random ones. So there will be a second choice that you're going to make. Do you randomly generate more if some were deleted? So this is another choice you're going to make. Because initially you randomly generate M, some may be infeasible, you kill, for example, 2 of them. Do you randomly generate 2 more to be sure your population always has M feasible ones? You can do that, but maybe when you randomly generate 2, one of it is infeasible again. Then you need to repeat this process until you are getting M feasible ones. So there could be a small while loop right here if you are writing a code. Okay? So now for my introduction, let's just assume after this process you are having M feasible designs, but they are not optimal. They are just feasible. Okay, what do you mean by feasible? Satisfying the constraint, but not the minimal F. So what you will do next usually is so-called evaluating the fitness. So this term came from the genetic story. So it's like checking whether a chromosome is fitting the world, how it is it's like a survival rate, something like that. So they use the term fitness. But what does fitness really mean? So usually it's defined by the objective function. And it's like a score, okay? So let's say you're minimizing an objective function, you can give it a good score. So in your coding, is larger fitness a better, larger score a better fitness, or lower score better fitness? It really depends on how you code. Again, this is where you make your own decision of coding. Okay. Usually, people in GA, they choose higher score as better design. There's a reason, because later on they are going to do some selection and they are trying to choose the one with better score, which means larger numbers. Okay, so if you are minimizing an objective function value, then right here you are going to maybe put a negative sign here, or do some kind of mapping, convert your smaller the better objective function value into a scoring system, which is higher the better. Okay, so here is another user-defined area that everyone's code may be slightly different. Okay, so once you give a score, there must be good ones and bad ones. So the next step is so-called the selection. Okay. So in the selection process, there are so many different kinds of ways to select. What does select mean? Selection in the genetic story is like if you have good genes, you will perform better in the world. You have greater chances to survive. So this selection usually has certain factors of probability inside, and the probability usually depends on how well you survive the world. So which value defines how well you survive the world is like the fitness, the score. So usually higher the score, you are going to be selected with a greater probability. Okay, so there is a very common way for the selection is called the Russian roulette selection. Russian roulette, like people use a gun and rotate the how do you call it? Spin the circular thing, and then see if you are lucky enough to kill yourself or kill others. So they call this a Russian roulette selection because there is a probability inside. So usually over here I would like to draw a picture. Okay, and it's gonna be like a pie chart. Okay, like a pie chart. But in coding, you don't really draw a chart. What happens is you can sort all of your chromosomes in a certain way based on their fitness score. So this particular one would be the best performing chromosome out of the M chromosomes. So why is it the best performing? Basically, it has the highest fitness value. Okay. So you will give this best design a greater pie. Give it a greater probability to be chosen. So the one with the lowest fitness score will have the lowest selection rate. But how do you define the selection rate? There are tons of ways to define this. Okay, so you can design your own way. For example, there are people doing this. The probability, let's say Pi, equals to sum of the fitness value, all of them, and also, I should say, the fitness value of the ith design over the sum of all the fitness. There are people doing something like this. So basically, if your fitness value is 100 and the rest are just 1, sum would be maybe 110. and your chances to be chosen would be 100 over 110. Then this particular design will be having a super high chances to be selected. Okay? So people define their own way to define this probability. So once they define the probability, what they do is they use a random generator. And like randomly pick a spot out of the pie. So let's say degree wise, if you say this is a degree 0 and you are going to spin by 360 degree, and you randomly generate an angle from 0 degree to 360. So whenever, the random generator gives you 10 degree, then you fall into one of the pie. The idea is like that. Okay, of course in coding, you don't really need to set up the range from 0 degree to 360. But the concept wise, it's like it's a wheel with different size of pies, and every pie represents one of the chromosome. Better ones has a greater share. Okay, and the random generator just randomly select. Since you are randomly select out of the based on their probability to be chosen, maybe the good ones could be chosen twice or even more. And in the selection process, it's okay. Usually it's okay. It's allowed to select the same design multiple times. Does it matter if you choose the same design multiple times? It is fine. Because later on there will be some other process that allows designs to be modified between different designs. So the more good designs you have, the better. But if you have too many good best designs, then you lose your chances to be finding even greater designs from the random process. Okay. So the goal of this random selection usually at the end is to get M designs as well. So now you're selecting out of the pool from this probability wheel. You're going to randomly generate M positions. The good ones may be chosen multiple times. The bad ones may not even be chosen once, but that's fine. That's a concept of random process. Okay, now you get 10 chromosomes out of the wheel. So what do you do next? Usually what you are going to do next is so-called a crossover. So what does crossover mean? Crossover means you are going to randomly pick up two chromosomes and decide whether these two chromosomes is going to exchange some numbers. So you randomly pick up two chromosomes. Okay, so you are going to have usually there's a pointer. And it's going to move from the first digit to the last one. Or the movement can be very random, but it has to go over all the positions. Every time you go to a spot, it's like you are rolling your dice again. You are randomly making a decision. Do you take a crossover process at this position? So usually there is so-called a crossover rate. So usually at every random pointing position, you only perform crossover when the random number is greater than the smaller than, usually is a smaller than, so-called the crossover rate. Okay, and what's the usual crossover rate? Something like 0.3.4, something like that. Like 30% of chances or 40% of chances I perform crossover. Something like that. Okay? So it doesn't happen every time. So the pointer could be moving everywhere. Every time you randomly generate a number from 0 to 1, if the number is 0.5, okay, you don't perform. Now move on to the next position. Roll the dice again. Move on. Roll the dice again. What if at some point, let's say right here, is satisfied, you are going to perform crossover at this particular position? What does it mean? Usually what's happening is you are cutting the chromosome in half and then you swap the body. It's like a worm you cut in half and then swap to the other worm and then put them together. So it's like a body swapping procedure. Okay, that's a so-called a crossover. Okay. So why does GA do this? Now we need to go back and think about the way we design the chromosome. So everything that we are not sure, we binarize them and we put them into a long string of zeros and ones. Later on, when we have the crossover process, we randomly pick up two chromosome designs. We randomly decide, okay, do you crossover? Oh, here, okay, let's do crossover right here. So whenever you decide to do crossover at a certain position, it's somewhere in between of one of your variables. So it could be like at the middle of your xi. And you cut xi in half, swap it with the xi from other design. And also when you do the swapping, one of the design was being cut in half, being swapped with body swapping with others, and also the entire tail of all the parameters was sent to the other design. So it's like this procedure has two, you should say, it will achieve two different things. One, that particular xi being cut in half will have a great change, usually a great change. So let's say one of the chromosome has a xi like this, the other one has a xi like this, and if we make the cut right here and then we do the swapping, see what happened. One of the design was having a number of 2. The other design is having a number of 255. When you do this changing, at the end, it ends up with right. It ends up with 2 new designs like the right lower corner. So the first design originally was 2. Because of the last 5 digits was changed to 11111, the magnitude of xi increases. And for the left one, it was 255 because the right 5 digits was changed to 00010, so the magnitude changes. Okay, so maybe the optimal design definitely is somewhere in between of those 256 combinations. And it's basically a string of 0 and 1s. So by this kind of random change, sometimes when you're lucky enough, you may get the good ones, some here, and the other good ones somewhere here. When you put them together, they become better ones. So it's very random. It's very random. So there's nothing smart about this. Really nothing smart. It's just a random way of changing the design. Okay? Okay, so this is one achievement this crossover get. Making a big change of xi. And also, when you do the swapping, because of the entire tail is changed to the other one. So maybe some other design has been set to certain values that is already good. So entire tail may be good right here, and the entire head right here is good. When you put them together, maybe this chunk of good genes and this chunk of good genes get together. So this random process make this possible, but it requires a lot of random changes. Okay, I'm going to get back to where we were. Okay, so this is crossover. So usually when the crossover is done, you are going to do something called mutation. So in mutation, you work on one chromosome at a time. And then again, you have a pointer. And then you're going to move around, and then you only perform mutation when this random number is smaller than the mutation rate. So usually the mutation rate is even lower, maybe 0.5, something like that. Usually very low. Something like that, or like a 3%. What does mutation do? Basically, what mutation does is convert 0 to 1 and convert 1 to 0. So it's completely mutating that particular digit. So let's say you have a string, and then you have this pointer randomly choosing its position. Every time when you move, you roll the random dice, see if it's matching the mutation rate. Because the mutation rate is low, so usually it doesn't happen too much. 3 times happening out of 100 times. Okay, so when you're lucky enough, okay, we decide to do mutation right here. So for that particular digit, if it's 0, convert it to 1. Or if it's 1, convert it to 0. So mutation usually allows big changes. But sometimes it doesn't change big. Why is that? So let's go back to see the definition of our chromosome. So think about XI. If one day your mutation asks you to change this digit on the very left from 1 to 0. In this particular case, it's a huge change. It basically cut the number of 255 in half. But if another day the mutation procedure changes the last digit on the right of XI, it changes very small. So mutation sometimes change a lot of things in your design, sometimes it doesn't. So that's the beauty of mutation. Okay, so once you're done, what do you do next? You will have n maybe completely different designs, right? And you are going to do fitness check again. You are going to see, of course, right here you can also do feasibility check. Because you may be randomly generating bad designs. Okay, so you do feasibility check, you do your fitness check, you give them scores again. So what's gonna happen is you're going to do something called the elite. You're going to keep the elite chromosome. So the overall best. You can keep 1, you can keep 2, but you decide how many good chromosomes is going to be kept. Okay, and then you move on to the next iteration. You go back to where? Go back to here. Go back to the next generation. So since you kept the elite one and move on to the next generation, it's like dinosaurs died, but cockroaches survived. So some kinds of animals survived to the next generation, some were dead. So move on to the next generation. The best one stays there. So now you may only need to randomly generate n-1 design because you have the elite design from the last generation. So you will keep on doing this. So whenever a generation found a new elite chromosome, it will be kept. So eventually, you will be finding better and better design. But it doesn't happen every generation. Sometimes the elite one, human right now, we can say human is the elite animal, maybe 5,000 generation. In the future, there's a different kind of species behave better, perform better than human, superhuman or whatever, mutated human. But so it's like concepts like this. Okay, the elite species, elite chromosome stays. So how many times do you perform this? You can do as many times as you want. So usually there is a max number of generations. So it's like when it iterate up to 500 iterations, stop. So how large this number should be, no one knows. Because it really depends on your problem and whether you're lucky enough. Okay? So I would say if you work on GA, you need to read some papers and observe what people has done to their problems. These researchers use population of 10, 500 maximum generations, crossover rate 30%, mutation rate 5%, and they were able to find pretty good designs. So my problem is having a similar scale of theirs, very similar type of problem. Okay, if I use the same setting, I should have the same kind of luck. I would say the random process should behave similarly. So okay, let's start with what they suggested on all the settings and then do my own coding. And once you're done, see if you can get a really good design. If not, okay, now let's change some numbers. Maybe I should iterate more. Maybe I should generate more per population. Maybe when I do the selection, I should allow greater pies for the good ones or smaller pies for the good ones. Or when I do crossover, maybe the rate should be different. Or I should use different kinds of crossover strategy. This is so-called the one-point crossover. There are people doing two-point crossover, meaning choose two positions and then cut that region and swap with the others, only that particular region, right? Mutate, okay? So there are many small things to define in GA. Now, I would like to show you what my lab member when I was a student did when she worked on her thesis. So let me change to computer and find this. Oops. Okay, so her name is Wei Ru, so she's from National Chen Kung University, and she went to Rutgers to study for her master's. This is her master's degree, defense. So she was doing a mechanism design. Okay, my advisor Hai Chang Jia, he's my PhD advisor. So I'm his senior. She's my junior. So she is trying to design mechanism. So if you are from Chen Yuxun's lab or Lin Yanhua's lab, you may be interested in this kind of problems. Actually, myself, Professor Lin Yanhua, Chen Yuxun, and Professor Xu Guanlun in NTU, we are still working on similar problems. Even for myself, I'm working on this particular problem in a 3D version. Okay. So the idea is how do you define linkage designs But in Professor Chen Yuxin's lab, she's from National Cheng Kung University, and they try to build up different maps of types of linkages with different numbers of links. So out of the available linkage map, pick up one or multiple of them and start to do shape optimization or dimension optimization. But in Lisa's work, she tried to avoid that kind of choices. She doesn't want to stick with the linkage map. So she gives GA the full power to randomly generate linkages. So her code will be generating a lot of garbage, basically infeasible designs, which doesn't satisfy the linkage map. But it has a lot of randomness that human usually can think of. So those random designs sometimes are interesting. Okay? So here, chromosome generation and feasibility check. Exactly like what I told you. She decided to, if this is for linkage design, so it's a planar linkage, so there could be multiple joints, and every two joints could be forming a link. So the decision of whether a link is generated is going to be described by 0 or 1s. So in this particular case, if the program decides to have 4 joints, the total combination it will be combination 2 out of 4. So there are 6 different links, and so she decided to define 6 numbers. When they are all 1s, that means all 6 links are connected. If one of it is 0, then that corresponding link will be taken away. So in this way, she can occupy 6 digits to define how the links are going to be occupied. Is this the only way to define a linkage mechanism? No, but this is her choice. So that's why whenever you use GA, you need to precisely carefully describe how you define the chromosome. Otherwise, people cannot follow you, cannot understand how you perform GA. So second thing she's going to use the binarized code is the position of every joint. So in her particular example, she used 10 different digits to represent the x or y coordinates of every joint. So if she has a 8 joint mechanism and it's in a planar problem, that means there will be 16 x and y's, and every one of them occupy 10 digits. So for positions, she's already occupying 160 digits to describe the positions of 8 different joints. Okay, and then for mechanism design, whenever there's a joint, the degree of freedom could be different. Sometimes it's like a fixed point, sometimes it's a free point, sometimes it's a slider. So in her design, she decided to have 4 different types. So those are like choices that I mentioned earlier. So whether it's fixed, X slider, Y slider, or free. Free means it doesn't. When later on when she solved kinematics, the joint can be freely moved anywhere. Okay. So for every point, she used 2 extra digits to define its type. Is this the only way to define it? No. And are those 4 types the only 4 types that you can define? No. There could be more. Okay. So later on, she will do feasibility check. For her problem, there are 2 things to be worried about. One thing is whether the mechanisms are linked together. There will be a scenario where some linkages are not connected together. They are like isolated links. So whenever this is happening, she will consider this as a poor design. Okay. So she did some kind of tree search to figure out whether it's connected. Then for like a traditional mechanism, she wants the degree of freedom 1, so she used the degree of freedom equation to compute for the mobility. She only allows degree of freedom of 1. Okay. So next will be the fitness. And in her thesis, she has 2 different kinds of problems. One is if you have this is like an initial design, and what these arrows means are like the input. So if she performs some kind of linear motion of A going left by certain distance, and if she treats position C as a output point, and whenever there is a movement like a mechanism, the target position will have a label, a symbol of C prime. So she will compute the distance between C and C prime. As long as in her first kind of problem, she just wants the movement to be as large as possible, maximum output. Okay, so why is she making this? She's trying to design a gripper. Okay, and sometimes you want this, you want the input to be small, like a small pulling force or a small motor, but the output is a big. It's like you can amplify your movement by the geometrical design. So the other kind of problem is maybe there is a desired position for C. We call it C double prime. So after kinematics, you compute the output position, and you compute whether C prime is close to C double prime. So over here, the distance, the smaller the better. So that's why she put a negative sign here. Smaller the better. Yeah. Negative, yeah, smaller the better. And with negative sign, the smaller the better. Okay? That's what she did. Next, it's about kinematics. It has nothing to do with this course, so I will skip it. She did some kind of finite element kind of analysis, so it has nothing to do with this course. A lot of math and solid mechanics. So I'm skipping this. The goal of this part is just to perform kinematics. Okay, So she did the Russian roulette selection, just like what I mentioned earlier. But in her case, she used minus. What is I? I should be the thinness. So if you use an n minus I, what does it mean? Her I is greater the better, right? Oh no, n is the number. She sorted. She did the sorting. So I think after sorting, n minus I. What does it mean? I don't remember. I need to read her thesis. I don't remember what she did, but I think she did some kind of sorting. Anyway, her crossover rate was 60%. She used a single point crossover. Mutation was only 2%. Okay, so this is an example where she wants for the problem itself, there's a fixed A point, a input point B. She's gonna rotate AB by a certain degree, so B moves to B prime, and there's a C point. She wants the C goes to C prime. Okay, and she's going to design a full bar linkage. So on the left is trying to illustrate that you can use a graphical approach to find where are all the join positions, and join 4 can be anywhere on this straight line by graphical approach. And from multiple performing processes of GA, she found different positions of point 4, and they all lie in this mentioned straight line, which means her GA procedure was able to find good designs, correct designs, just like how the theory tells you. Okay, full bar linkage. And this is a different problem where she's asking the full bar to move from one point to a C prime to a C double prime. So two desired positions. Graphically, that will give you the exact output position of actually the fourth joint right here. And from her code, she was able to find that position as well. Okay, so these two examples are like the first two examples she showed to clearly prove that her GA procedure was able to find the optimal solution, just like the theory. Now, she begins to design different things. She's looking for some kind of press mechanism where on the left hand side you may have in a reality you may have some kind of piston. You can press forward or move backward, and you want this press to like a downward movement to press maybe like garbage or whatever. So in her problem, she will have this point A going left or going right, point C stay fixed, I think, and point B going downward. Okay, so does the animation move? Okay, so this was back in 2008 maybe. When was she? She was in 2008, I think. 2008, yes. So like 17 years ago. So at the time when we generate video and put in PowerPoint, it doesn't play anymore in right now. So I think we were using like a very old codec. Oh, actually, it moved. Did it? No. Oh, yes. It is moving. It is moving. Okay. So, see, the input point goes right, and the output point goes down, right? It is moving. So this is input point going left, output point going down. Oh yes, it is moving. Okay. And take a look at the fitness value. On the horizontal axis, it's the generation. And on the y-axis is the fitness value. She took a logarithm of the fitness value. She did lower the better. So initially, the fitness was high, and then at some point you will see the fitness value stays for a while, for several generations, and then you see a sudden drop. Why is that? Because she kept the elite chromosome for and then moved the elite one to the next generation. So whenever you see a horizontal bar like this, that means the elite chromosome stay the best one for several generations. Up to certain generation, we randomly generate an even better one. So there's a sudden drop. Okay. So if she performed this GA for, let's say, 100 more iterations, can she find an even better one? Maybe. But if you keep on hoping you are going to find an even better one, then you may need to run so many generations. It's gonna be too many. Okay, and think about your design space. Let's come back to our iPad. So let's think about this. So let's say you have your chromosome length, for example, 200. Okay, so your solution set is 2 to the 200 solution combinations. Okay, and let's say every generation you generate 50 different chromosomes, and you are going to run the generation, let's say G, 1,000 generations. So how many solutions you have tried? So in total you tried 50,000 different designs. So basically this procedure tried 50,000 random designs out of 2 to the power of 200 solutions. That's what happened for the GA process. Okay? But go back and think about your gradient-based approach. Have you run this many solutions for gradient-based approach? No. Usually for gradient-based, you sample the points, including the small perturbation for finite difference. That counts 1, right? So usually, so let's say for my for Lisa's design. She has maybe 6 joint positions. So it's like 12 x and y's, right? So it's like you have 12 variables, and there are certain variables to be chosen. Like for every joint, you have one more for the joint type, and you have a bunch of them for joint connection. So it's like a combination 6 out of 2. So it's like this, 15, right? So joint type, you may need 6 variables. So in total, you may have like let's say 20 variables. Okay, and if you convert all variables into continuous variables, like like I said earlier, you decide to use a gradient-based approach. So 20 variables, and then later on discretize everything at the optimal. So if you do that for finite difference, let's say you use a second order procedure. So the amount of function calls per iteration is like 2 times variable plus 1 plus every select 2 out of n. So that's the usual number of function calls you need for second order finite difference. So in this particular case, it's like a 2 times 20 plus 1 plus 20 times 19 over 2. So it's like a 40 plus 1 plus 190. So it's like 231. So every iteration, you evaluate the function 200 something times. For gradient-based approach, let's say you use 10 iteration. So you evaluate the problem maybe 2,000 to 3,000 times, compared to GA 50,000 times. Okay, so from here you can tell for gradient-based approach, usually you don't use that many function calls, but you are trapped at the local. If you want to use GA, okay, you require more combinations, more computations, but you won't be trapped at the local. You should be able to find somewhere close to the global, but no one guarantees that's the global. No one knows, because the total combination of solutions are 2 to the power of 200. So many of them. You won't be able to examine every one of them. Okay? So every time you make a decision of optimization methods, don't just think of, okay, this is something I'm going to use. Okay, run it. Get a solution. Okay, good, I'm satisfied. Don't do that. Think more about the process. Make smart choices. That will help you in the future. Okay, so that's everything I want to mention today. Do I do coding? I may not have enough time. Let me use I know I have a old GA code that I show the students from the past. Maybe I can open that one. Need to turn off. I'm not sure which one is good, so I'm gonna. Okay. I'm not very sure. No, this is not. This is not the one. So maybe this one. Okay. GA. Okay. Let's take a look. Okay. So I used this earlier. I was solving an optimization problem with a objective function right here. Do I have? I need to see where I have constraints. I think I have constraints. Let's run the unable to separate the syntax. Dash. Cannot do the dash. So I need to. GA. Okay. Here. Maybe we cannot even do the dot. So maybe this one better. Okay. symbolic, so it takes some time. I don't remember what I did. Okay. So there's a nonlinear objective function, and there's a nonlinear constraint like this. So usually I'm minimizing, so the left lower corner direction is the minimum objective function direction, but this constraint is like a ball holding it, so the solution would be somewhere here. So I was using GA to see if GA can find a solution here. So over here I had a population of 50 and 500 generation, crossover rate 30%, mutation rate 5%, utilized 20 digits for I think accuracy of X. So right here, as you can see, for every population I will have a flag to see whether the design is feasible or not. So initially the flag is 0. While the flag is 0, and initially k equals to 1, so it goes down to here, it will randomly generate basically 20 0 and 1s. So if you take a look at X, I use a cell. It's a 1 by 20, a string of 0 and 1s. If you take a look, X, a bunch of 0 and 1s, randomly generated. So for every design, I perform so-called a feasibility check. I think I convert binary to decimal. So 10 digits for X, 10 digits for Y. So at the end, X1V, X2V, they are the X1 value and X2 value. So that random point represent 23.1672 and 24.1447. But so I plug in. Here's the constraint function. I think I plug in to see whether it's feasible or not. So after plugging in, not feasible. So, because if it's feasible, it will get into the if loop. So not feasible. So it will go back to here again, go up. Now k is still 1. So I will keep on generating feasible points until I have how many? No. This is still. What's my I? I is still 1. So I will keep on generating feasible designs. When it's feasible, I will check its fitness. So I will try to stop here. So at some point, I randomly generate a design 82.89 and 81.91, and it satisfies the constraint. So the flag becomes 1, and then I will check the fitness. So fitness basically is my objective function. So I plug in and then I get a fitness value, super large. Okay. And so I will keep on doing this until how many of them? I will have 50x1 and 50x2. They are all values which satisfy the constraint, and they all has fitness value. And some are large, some are small. So I evaluated the maximum value is like 5 to the 10 times 10 to the 4th. Minimum is like a 6 times 10 to the 3rd. So because I have this quadratic function, so when you plug in the value, the scale is very wide. And what I did was I think I compute some kind of value to define the selection rate. So this D value is gonna help me to define my selection rate. So I sort this D value. This is like a sorting of the thinness. So percentage wise, let's take a look at so-called the percentage. I have 50 chromosomes. The first one is my best one. It has 4.7% to be chosen. My last one has 0. Because I have 50 of them. So every chromosome has a very small chances to be selected. Now, I will perform selection. So here I will generate random numbers and then select. So anyway, it's based on the percentage. Okay, so complete selection. After selection, selected ID. Let's take a look at so-called the selected ID. So I had 50 of them. These were selected. Are there any one being selected twice? Yes, you can see there's a 5. There's another 5 down here. So the 5th chromosome must have a pretty good fitness value, so it was chosen twice. Or the 5th chromosome was lucky, just being chosen twice. Okay, so here I perform crossover. I think I did so I made some random process for the crossover. So anyway, crossover done. And here is what did I do? After crossover, I evaluate the positions. So I think in the past I did some plotting. So I think I should show you the plotting as well. So let me turn off the code and then open the plotting. So then you can see how the design points were changed by different steps of the GA. So you can visually see everything. So right here, okay, let me continue. These are the 50 feasible chromosomes. The corresponding true positions of the 50 randomly generated design points in the feasible space, because I did the feasibility check. Okay, and then I will make a plot right here. I think I plot out the overall best. So actually, out of the 50, this one is having the greatest fitness value, which means the objective function value is the best. Okay? So continue and then perform crossover. Okay, let's perform. Did I do some plotting here? No? Here. Okay. So it will be interesting to take a look at the result of the crossover. Yeah. So all the green crosses are the new design points based on crossover, or the green crosses. So, is there any green cross that is very close to the original red dot? Here's one. I think they are the exact same point. You cannot see it. Do you see it? This particular one, this is green cross on top of a red dot because the marker is so small. So that must means that particular chromosome is so lucky it was not crossovered through the crossover random process. Okay? And then what? Mutation. So let's take a look at what's gonna happen after a bunch of mutation. So the mutated ones were being highlighted by the black square. So you can see this particular one. I think it's a black square on top of a red cross. Okay? So basically a bunch of random process. But it did explore somewhere within the invisible space because the crossover procedure and the mutation procedure doesn't guarantee to stay invisible. It's just randomly explored. Okay? So here I perform fitness check again. So let's stop here. What happened? After all these, this is the overall best. So actually, the initial best is even better than the resultant best, because this overall best was being modified by crossover mutation. So at this point, I feel like it's such a pity that we actually found an even greater one. So if I'm the programmer and I see this, I may change my coding again. I will maybe at least compare the fitness of the overall best and the fitness of the initial best. If the initial best outperform the overall best after crossover mutation selection, then I want to keep this one. So in my earlier code, I didn't do that. I allow the GA process to randomly do something, and so my original random best was being modified and then become worse. Okay, so here is where you can do better in your coding. In the past, when I taught this course, I didn't see this. So at that time, I didn't do that. But now I realize, hey, the code could be better. So let's turn off the green cross and the black marker, because if I keep on running this code, it's gonna be a mess. So let me turn off some of the visualization. I think we can turn off. This is the feasible ones. We can turn off after crossover. Don't plot again. After mutation, don't plot again. But I think we plot out the overall best. So the blue circle is the overall best from the initial random process. The green circle is the overall best from the all the random process. So let's observe the movement of those blue circles and red circles. So let's continue to see if I continue the code. So you can see that the random blue are quite random. Every time it could be randomly find something within, definitely within the feasible space. It's sometimes not very good. Sometimes it's not close to the optimal. But the red should be quite close to the optimal. And the red one keeps the elite one from the previous. So it should be getting better and better, not worse. Okay, finished. I think we can turn off the blue so we can see how the population generation is improving from the elite ones. So let me turn off the blue. Just observe the red. So sometimes it doesn't change much. Sometimes it doesn't find an even better one. Sometimes it does. Finished. Okay. So this time, you can observe what I had earlier. It was 66.8 and 15.15, and the second time I run it is 63.44 and 17.3. They are not the same. The objective function value is 55014 and 5521. So the earlier time actually found an even better one. This time is not the overall best. So this is the issue of GA. You are not sure if it's the best. So let's run the code again. But this time I think we don't need to see the visualization. Or we just see it, that's fine. Let's see if we run the code 3 times, can we find an even better solution. This time is better. The objective function value drops a little bit. So maybe if you are running a GA code, you want to run multiple times, just to be sure. Maybe. Right? Okay, so this is my demonstration of the GA code. I didn't have time to write it again live. But if you go to the course web page, this particular role and this particular code, it has actually, if you go there, it has a bunch of codes that I wrote in last year. But when you download the code, every code that has a number in the first character won't run in MATLAB. So you need to change the file name. You just remove the date. You cannot have a M file with a number in the front. It's not okay for MATLAB. Okay? Any questions? Okay, so that's it for today. Next week we have the makeup exam, right? I promise to make it simpler. So see you next time. Good luck. The coverage of the problem will be the same. Basically same kind of problems, but simpler.